Good day to everyone. This is the rebase talk by Christian Hummer. He's going to talk about Graal and Truffle. Christian is from Oracle Labs in Zurich.
Okay.
I'm sorry, I had several YouTube tabs on. So yeah, so we're here with Christian Hummer from Oracle Labs in Zurich. Christian graduated in Linz with the Graal group over there, or well, what do you call that group?
GraalVM group.
Right. And you're one of the developers of the Graal at Oracle Labs. And
yes. Go ahead.
Go ahead.
Yeah, I'm part of the GraalVM team that is spread all over the world. Yeah.
Right. All right. And so you have prepared a talk for 40 minutes, but we actually have a slot for 80 minutes. So I think we have time to explore this and to learn all about Graal and Truffle. I propose that people ask questions in the chat on Clouder or here in Zoom. And I don't know, I like these things to be interactive. I don't know, Christian was a bit hesitant about that, but I think it would be useful to have a conversation about Graal and understand what it's all about. So I would propose that we take questions and yeah, so go ahead, take it away.
Let's do that.
Christian.
Okay. Cool. Thanks for the introduction, Nicole. So the talk is towards the Tower of Babel, a polyglot language VM in Java. And I need to show the slides, so don't trust anything I say today. So my name is, you already introduced me. My name is Christian Hummer. I'm industry researcher / VM engineer at Oracle Labs in Zurich, working on GraalVM for the last 8 years. And currently I am the Truffle framework lead. Previously, I was also working on the R language or also on the JavaScript language a little more. So since the talk is named towards the Tower of Babel, not everyone knows that story. I would just quickly explain it to you for your entertainment. So the Bible tells the story of a group of people that is heading east to build a city where all people speak just a single holy language. And the language goes that they're not just building a city, but also this nice tower that you can see here on the picture. And the top of this tower was really impressively high up. So high up, in fact, that it almost reached heaven. So one day, God came down from wherever he comes from to the people and looked at the city and the tower, and he did not like what he saw. So he thought, if they can build a tower so high, they won't need me anymore soon. So he decided to confuse the languages of all the people such that they don't understand each other any longer. So this quickly brought the construction of that wonderful tower to a halt as everyone got confused. So confused, in fact, they spread over all the entire world. I think you can roughly see where I'm going here. If you want to build a Tower of Babel, but how can we continue the construction of the Tower of Babel if there are so many programming languages out there? How can we construct the Tower of Babel with so many languages? So one question you immediately might want to raise now is maybe we can agree on a single language, the ultimate programming language. This question was asked on Stack Overflow, and some moderators think that it's not a constructive question to ask. I personally think it is a valid question to ask. But from the current state of the art, if you just look at the different developer communities and how many people speak different languages, I don't think there will be the ultimate programming language that will handle all the programming environments well anytime soon. So if there cannot be that single programming languages, maybe there can be a single polyglot virtual machine. So to say, maybe a polyglot virtual machine to rule them all. But we first need to establish why I think this is a good idea. And some of these ideas will follow through the entire talk. So the first thing is, it is about feature parity between languages. So if with features, I mean performance or tooling and things like that. So when you think of this problem, you should really not think of it as a single application, right? You should think of it more like as a set of application. Think of the Tower of Babel as a set of application and not just a single application to build. So most likely, in a big enough project, you end up with like 3 to 5 different programming languages used in a wide variety of applications. They all use different tools. They all have different performance characteristics. So you're effectively restricted in the choices you can make here. So I think with a Polyglot VM, we have and having tooling and performance efficiently solved by both for all the languages, we can choose the right language for the right reasons, and we should not be limited. Sometimes I feel like whenever there is a new language that becomes mature and has proper performance and proper tooling, it's mostly already obsolete. So this is typically that happens right after. So ideally with the Polyglot VM, we can reuse that tooling, provide good performance mostly out of the box much quicker than if you would build a specialized VM for a language. The second big thing is reuse across VM implementations. Everyone that works in this field knows that tooling, fast compilers, sophisticated GCs require a significant amount of effort spent, which is repeated for each language-specific VM. A new compiler or GC optimization can often take years to finalize and get into mainline. So the goal of a Polyglot VM is really that we don't need to redo this work every time when we need to implement a new language. So ideally, the runtime system, the GC, the compiler should all be shareable in a Polyglot VM. The next step is reuse across language ecosystems. This is, I think, what people immediately think about when they think about a Polyglot VM. You have that one library written in that language that is good for plotting, and you have that other language that is good for number crunching, and you want to use them together. So most languages currently are not very well embeddable, so they currently need to run in separate processes, making calls between them very expensive. You cannot really optimize across both process boundaries, and I don't think you can even think about having a debugger that goes across multiple processes. That's really hard to do. So a true Polyglot VM allows you to optimize across this tooling, optimize across the language boundary, and provides tooling there. So I don't want to have this misquoted. I don't want you to use multiple languages for the same, necessarily for the same application if it's not something you need to do, right? So it's still best to write your application in a single language. But again, you need to think of this as a suite of applications that enables you to use that one library in that one language written by a different engineer that knows Java, and that other engineer knows JavaScript, and they can work together. So this is a very interesting and I would say rather new field of active research. There is a lot of unknown, not really answered questions. There is, how do we do polyglot package management? How do we do testing? There is a lot of things that's going on in there currently. But it's also very fun to see because you can really do new things that were not possible before. The next thing is why Polyglot VMs is a good idea is we can actually build an embedding API that is language agnostic. So you basically embed your language once and get all the other languages for free too. So this is interesting for Oracle, because I work for Oracle. We want to integrate that into complex systems like the Oracle database, and we want to not redo this all over for every language, but we want to actually share a lot of the effort we've done there. We have this multi-language engine where we actually do that. So yeah. So the next and last but not least, we also want to encourage language specification. We have really learned from JavaScript, C, and Java that multiple implementations are really beneficial to a language ecosystem. With so many implementations, the performance and the tooling really thrives normally. This is because language designers need to be very precise in the features they specify, and they are forced to not keep everything up to unspecified behavior. A Polyglot VM benefits a lot from such a language specification, but we think also the languages benefit a lot. So it's really a win-win situation. So I think maybe if you do a new language, you should not just go ahead and do a language specification maybe immediately with the first release. But when you go and say your 1.0 release, I think a language should also have a language specification and actually maybe have not just one implementation, but two. When I talk about language specification, I also mean the native interface to extend the language. Most of the languages have an extra API to call into native libraries, and many languages don't really specify that very well, and they just expose implementation details of the original runtime there. So I hope I convinced you a little bit that polyglot VMs are a good idea. So now I will tell you a little bit more about GraalVM. GraalVM is our approach to a polyglot VM, but in the public, GraalVM is known a little bit more, to be known to be a little bit more. So we currently differentiate here about 3 things. You can use GraalVM as a drop-in replacement for your Java JDK. Ideally, the Java code just becomes faster because it uses the Graal compiler, which is a new just-in-time compiler we are building as part of GraalVM. And we also have a tool called Native Image that allows you to ahead-of-time compilation of Java, so you can create standalone binaries that don't need their JDK anymore. They have low footprint and very fast startup time. And we also use that Native Image tool in our Polyglot VM, actually. This is pretty popular these days in the microservices area, where they are really excited because they finally can compile Java code to native code efficiently. But the thing we are going to talk about today is the high-performance polyglot VM aspect. That's the more ambitious part of GraalVM, where we really want to. It's kind of the long shot where we really want to change the status quo. Okay, so on the bottom in our system, we have a Java VM. It runs on top of the Graal compiler. The Graal compiler is written in Java. Then you have also all these JVM languages that can run on top of it. But our Polyglot VM is called the Polyglot Truffle runtime. Runs on top of that, is also implemented in Java, and it allows languages to be implemented on top of that system. We currently implement 4 major languages. This is R, Ruby, Python, and JavaScript. JavaScript being our most mature language. And the reason JavaScript is our most mature language is because Ruby, R, and Python, they all have very sophisticated native extensions that we also need to consider running for completeness, so we actually can run applications out of the box as drop-in replacement. And in order to run these native extensions, they all have the same problem. They all expose internal implementation details to their native extensions. So we kind of need to emulate that behavior in order to get compatibility and to get this running. So in order to achieve this, we need to run a lot of C, C++ code on our platform too, because we need to have this emulation capability. So we also implemented Sulong, which is our LLVM bitcode interpreter that takes LLVM bitcode spit out by C, C++, or R and interprets it and runs it on our platform. Recently, we also added the capability to run WebAssembly code. So we can also just take WebAssembly code and run it there as well as an alternative. And also, we want to bring Java onto the same platform with a new JVM that we call Espresso. We didn't talk about this much about public yet, but we will hopefully soon. It will enable us to run all the Java languages on the Polyglot Truffle runtime. So let me quickly highlight what is Truffle doing differently than other specialized. Sorry, again?
Can I quickly interrupt you? Can you do the previous slide? Why are you duplicating the picture you have on the left, on the right?
Because that's a good question, because when you now call from a Truffle language into the host language, we have some overhead because we do a Java call, we have a transition there. Also, when you call from the host language into Polyglot Truffle, we have some overhead. The Java hotspot implementation that we typically use is not very well embeddable, so you get all these reasons why you want to have a language there. I mean, it's basically all the reasons we had on the slide before, right? We want to have tooling across the language boundaries here, right? That's why we want to put it also in the Polyglot VM.
So you get interaction between, say, a Java program and a JavaScript program, or
exactly. We have it to some extent, but currently you cannot, for example, use a Java debugger and our debugging, right? And then switch between them very easily, right? So if we run Java also on our platform, we don't have the problem. We can just use the debugger, and it's just the same debugging mechanism.
but it would seem you would get a whole lot of overhead.
Would seem so, but actually Truffle and Espresso is pretty efficient, but I cannot talk too much about the numbers there yet. Okay, so what is Truffle doing differently than other specialized VMs? So one of the things is compilation using Futomura projections. Normal interpreters or normal runtime systems, they typically write an interpreter that specifies the semantics of the language. And then you also specify a compiler that takes the EST of a language and also produces optimized machine code from it. So you basically need to duplicate the semantics of your language. In Truffle, we are not doing that. We are basically generating the compiled code from the interpreter directly from a single specification. I have an example of what this means in the following slides. The second important thing is we do dynamic speculation and automatic deoptimization. Dynamic speculation is something that more platforms do, but the fact that we only need to specify the interpreter makes it much simpler to perform the deoptimization steps. In other runtimes, it is very complicated to go from the optimized machine code back to the interpreter, which typically requires significantly a lot of engineering, but with the one specification, we just need to call a function and Truffle is doing everything for you there. I also have an example for that later. The second thing is language composition. We actually specify an interoperability protocol that allows you to use languages together and also inspect languages in a language agnostic way. So you can, this is important for the embedding aspect, but also for using languages together. The next thing is tool composition. I mean, the tools themselves can use the same interoperability APIs that we use for language composition, so they can inspect values. On top of that, tools have an instrumentation framework where they can, in a language agnostic way, inject, add additional behavior to Truffle interpreters without actually knowing which language runs underneath. So we can actually implement a single debugger for all the languages. That's kind of the idea, and also a sampler and so on. And last but not least, we have that Polyglot embedding capability that I was talking about in the beginning, and we are also exploring actively how we can run all our languages in a sandbox environment so we can run untrusted code. Let me start with Futomura projections that might not be known by everyone. So Futomura somehow investigated 1971, so this is really old theory, investigated the relationship of semantics of programming languages and an actual compiler. So he found that a compiler can be derived from an evaluation procedure, which means the interpreter, instead of conventional approaches where the translation is described directly. But I found explaining the Futomura projections is always best going through a concrete example. So I will do this with a simple Truffle interpreter here. Elko said in the beginning, Truffle is often a little bit of magic. So I'm trying to be very concrete here. So first, I need to say that in Truffle, you can write your interpreters either as bytecode interpreters or as EST interpreters. The bytecode interpreter does not fit on a slide, so I show the EST interpreter version. We're currently not fully decided yet which version is best. Bytecode interpreters has some footprint advantages. Performance-wise, they seem to be very, very close to each other. So, for example, we have WebAssembly interpreter is implemented as bytecode interpreter because it's already a bytecode specification. Also, LLVM is implemented as such as a bytecode interpreter. But JavaScript is naturally expressed as an EST interpreter, so it's implemented as an EST interpreter. All right. So, what do we?
A high-level question about that. So, if you write things as an AST interpreter, it seems that you follow the control flow abstractions of the host language. Is that the? I mean, so for example, if you wanted to do continuations in your language, would it be easy to do that as an AST interpreter?
Continuation is definitely easier in a bytecode interpreter than an EST interpreter. But if your host language has no continuations, right?
Right, but the host language is Java, right? Or is it?
Yeah. You cannot just in the middle stop and continue execution. If you mean that, yeah.
Well,
yeah.
Go ahead.
So yeah, control flow in EST interpreters is typically handled through exceptions in Truffle, whereas in a bytecode interpreter you can directly handle the dispatch in the bytecode interpreter loop. We found that handling this using exceptions in the EST interpreter is pretty expensive, also on Java. And so we are currently migrating more towards where we want to avoid exceptions as much as possible. And this might be one reason why bytecode interpreters ultimately win. We are not fully decided what to do. It's definitely easier to write an EST interpreter, in my opinion, to get started. That's why I also use it for examples always.
Yes, I agree. But then you're limited in sort of the control flow paradigm to what the host language supports, right? And,
yes, you're limited to that. But with exceptions, you can actually emulate a lot of things.
Yes, but then at a performance penalty.
At a performance cost, yes.
Right.
That's true.
Okay.
Okay. So yeah, so we have this expression node. It extends node. Node is a Truffle class. We just specify an execute signature. And for simplicity in this example, I just pass in an integer array for arguments and return an integer value. Normally, you would have here an object value and a virtual frame to have the capability to read, write local variables. But in our toy example here, we just use simple expressions, so we don't need a frame, and we just pass in the arguments very simply. So that makes it explaining a little bit easier. So the first, and it actually fits on our slide. So the first node we are defining here is an add node. It just has two child expressions, left and right. And then when we execute it, we just execute the left operand and the right operand, and then we add both expressions together using normal Java addition. So one thing to note here is that we have added these child annotations to the fields. And that means that we consider whatever is stored in the left or in the right field is part of the EST. Why this is important, that we will see in a second. And the last node we need is some way to access an argument in our arguments array. And here we have an argument node, you pass in an index, and that just indexes, reads directly from the arguments array and returns the value. So we also need, for example, is some entry point, something how we can trigger our interpretation. So in an EST interpreter, all we need to do is basically call the execute function of the root expression, and it just propagates recursively and evaluates your expression. And here, the interpret function takes the expression and a set of arguments. What we also need, for example, is a sample program. I really just use a very, very basic sample program where we just basically add all the three arguments up. So we have an outer add and an inner add to handle three variables that are added. Okay, now comes the interesting part. This is how do we actually compile that Truffle interpreter now to optimized machine code. And so we take our sample, we have our interpret function, and what Truffle is doing, it's applying the first Futomura projection, which is effectively the partial evaluation of that interpret function with a constant AST, with our sample AST in this case. So what you get there is you get an interpret sample function that now cannot just take any AST, but just this one AST and executes it. So an important thing to note is that Truffle doesn't generate Java code or anything like this. So this partial evaluation step is actually something that happens in the compiler intermediate representation. So you don't see that. But for these slides, I just produced some Java pseudocode so it's easier to understand. So now we get this interpret sample function that directly calls into that sample constant execute. And what partial evaluation now can do is it can further optimize this down. And how this optimization works is you take this interpret sample, and since this sample is now a constant, a compiler can now just inline the execute method of the outermost add. And that basically just takes sample.left.execute, sample.right.execute, ends up. So now it's important that we had added these child annotations, because the child annotations say whatever is stored in that field is now part of the EST. So the compiler also considers that a constant. So whatever we read there is a constant. So we can then follow that we can also inline the execute methods for left and right. If we inline the left execute, we end up with another two nodes that we're executing, the sample.left.left execute, sample.left.right execute. And also for the last node, we get the arguments access with arguments sample.right.index. So the next step is we just inline the remaining execute methods. So we have 3 arguments accesses like in the last one with different indices. And now since sample.left.left, they are all constants, and index is a final field on the argument node, we can actually all constant fold the values of these final fields, and we end up with the final program that we want to see in the compiled code. So this is what happens underneath in Truffle, like on a very basic level, but it all follows from that. So this is the fundamental process that we take, and this doesn't. So this is because of this, we don't need to specify a compiler. All right, so let me quickly summarize the Futamura projections. So there is partial evaluation going on. In general, partial evaluation is just taking a function, specializing for some static input or constant input, as I said, and you get a specialized program. And then the first Futamura projection is the thing that we actually apply here. It's the partial evaluation of an interpreter given some source code. In our case, we already have the EST, yielding an executable. One thing I forgot to mention is we started with an EST, but normally in a language implementation, you would use some parsing. Truffle doesn't actually have some opinion on parsing. You can use whatever framework you want for that purpose. Important is that you can build an EST out of it in the end. And besides the first Futamura projection, there is also a second Futamura projection that I cannot do an example on, but it's still very important to note, is that you have the disadvantage with the partial evaluation normally that this is slower than a specialized compiler. Because it needs to interpret all these functions, needs to constant fold the fields and so on, and needs to do this in a generic way to handle any EST nodes. But you can now apply the second Futamura projection, which is basically the partial evaluation of the partial evaluate function itself, but you see now the add nodes, the nodes that this partial evaluation function are now constant. So you can then basically, if you interpret the partial evaluator as an interpreter itself, you can then apply the first Futamura projection as the partial evaluator. So you can think it like this. So in the end, you get a specialized compiler out of it. GraalVM doesn't do this at the moment. We have several prototypes that try to do this. We are not quite there yet, but our partial evaluation, our generic one, is currently also reasonably fast, but obviously we want to get to the specialized compiler performance in the end, ultimately. Would be a good point for questions. Okay.
There's some questions on Zoom chats. Let's see. Fabio, you want to comment on continuations?
Not really. It's basically just what Christian said. As part of implementing a Smalltalk for the GraalVM, well, we built Truffle Squeak. We had to find a way to support continuations, and we're using exceptions for this. I only shared the corresponding paper in the chat.
Right. And
maybe Project Loom will help us in the future to make this easier. That is adding continuations to Java.
Right.
And what is the cost of those, of using exceptions to implement continuations?
It depends. For the system, it's not a problem. We can just use it and it's fine. There are other problems that are harder to deal with than continuations, but they work fine.
I think it definitely has an impact on the interpreter performance that Fabio couldn't really measure that much yet because it might be dominated by other things like boxing in the interpreter. But most languages, when they measure performance, they go very quickly away from the interpreter to optimize code. So the interpreter performance doesn't matter that much. And in the optimized code, we don't have these exceptions anymore, right? They go away, they are optimized away, and they are just normal control flow in the end.
Right.
Okay, and let's continue.
Other questions?
All right. Okay, then let's talk about dynamic speculation and deoptimization. Dynamic speculation is really important to implement dynamic languages efficiently because they have very rich semantics. For example, an addition is not just the integer addition I've just shown, but also a string concatenation or a double addition or any other redefined function that is happening on that addition, right? So what is really essential is that you need to speculate in the optimized code that you don't need certain overloads of a particular function. I have an echo on my thing. Okay, better now, thanks. Yeah, so what we do in Truffle is we typically start off with an uninitialized AST, where we don't have the information collected yet, and then we execute the AST just like in a normal in the AST you have seen just before. And then we collect some profiling feedback in the AST nodes. You can think of this just as fields that are stored in the AST nodes. And so we run the AST nodes for a while. Some nodes might specialize on strings here. Some nodes might specialize on integers here. But it's just examples. But at some point, when we execute an AST often enough, we actually trigger this partial evaluation, first Futomura projection step, where we optimize the code. And in this step, we also assume that the profiling feedback is no longer changing. So we optimize with the profiling feedback, and then the things actually fold, and we only need to compile the string and integer cases. So, but as you can imagine, this is a speculation, so it might go wrong. And for example, if one of these integer cases suddenly gets a string value from the program, we need to deal with this case. And this is where deoptimization comes in. I was talking about this quite a bit, is where you then jump from the optimized code back into the interpreter, which is the Java program executing the AST. And we deoptimize. And then we need to also change the AST such that it can handle these new inputs. And then we would compile again with this additional integer and string semantics in that particular node. So one important thing is that this doesn't go on forever. So you should really stabilize in a finite number of steps. This is actually one of the challenges to get right in our Truffle interpreters is not like reach a stable state very quickly. Don't overly aggressively specialize, because then you always pay the price of the optimization if you're wrong. So you should really only specialize if you know it benefits and the compiler can do something with the information you provide. So let me also go through a concrete example here. So let's define a simple new operation, the same language we have already used. Here is the absolute node. It just takes a single operand that we execute, and then if the value is greater or equals 0, we just return that value, and if it's not, we just return the negative value, so we always get a positive number. Everyone has implemented that. So what we could do here now is we could specialize on we have never seen negative values, for example. This is just an example. In a real implementation of an operation, you would do more specializations like this, but we just take this one as an example. So what you would do there is you would declare a new field, the profiling feedback, so to say, that you annotate with a new annotation called compilation final. And in this case, we just declare a new Boolean, C negative. And then in the else branch of our execute, we just add this speculation in. So if we have never seen, if C negative is false, we call transfer to interpret and invalidate. This is nothing else than this automatic deoptimization I was talking about. So really just need to call this one function that's restoring the state, jumping from the optimized code back into the interpreter. And then now, since we are deoptimized and we are guaranteed to run in the interpreter, we can also modify this compilation final state. One important thing is that you never modify the compilation final state, you always need to deoptimize before that. You need to make sure that all code is deoptimized before that. So in this situation now, the compiler sees this absolute operation in two different modes. Either it sees that C negative was false, so the profiling feedback has never entered the negative branch, so we get this value greater equals 0, return a value, otherwise deoptimize or transfer to interpret and validate, but deoptimize is a little bit shorter. And the compiler can also see C negative true, then we get we get the full semantics of the operation. You need to understand that these checks, the if condition with the compilation final Boolean, they all fold. So if they become true, if C negative becomes true, the entire if condition folds away and the transfer to interpret and invalidate goes away with it. So why is the first version now better than the second one? And the reason is that the first one doesn't include the control flow for this operation. And the compiler can do more follow-up optimizations if it knows it's always just that value and not a computation that needs to be performed for that. Yeah, so this optimizes away nicely. Another good point for questions? Okay, then let me move on. Right, so how does compose?
Yeah. Can you go back to the, so are you actually getting rid of the condition there, or is that staying in the optimized?
Right, thank you. That is important. I forgot to say that. So this condition there will be turned into a so-called guard. A guard is in the compiler, so we need to check it, but we deoptimize if the condition is true. So the negation of this value greater equals 0 would be the new guard we would insert. So we need to check it still, the value, but we don't need to produce the operation.
The operation as in the else branch, you mean? Or?
Yeah, as in the else branch. We don't need to include that in that case in the optimized case. So you need to think of it.
So you get fall true, or well.
No, so yeah, basically it becomes the value becomes just the identity function, and everything that comes after that absolute instruction can just take the value directly and doesn't need to have a control. The compiler doesn't need to be. It's very much simpler to argue about this value for the compiler.
And the guard is kind of a trigger. I mean, it's an assert that.
Yeah, the guard is basically what the compiler implicitly generates from this kind of patterns. So if it sees this kind of patterns, it turns it into a guard. And it, yeah, deoptimize is a trigger that typically is operating system faulty page that triggers a signal handler that triggers the deoptimization. So we don't have a price to pay for that.
Mm-hmm. So is the guard operating sort of in parallel to the?
No, the guard is just executed before that, but our guards, they can actually float in the compiler graph, so they can be moved by the compiler up and down depending on the semantics of the final graph.
Right. So you still have sort of a conditional there, right? I mean, because
yes, you still have a sort of a conditional there. Yeah, that's left. But depending on the semantics, the conditional might be eliminated because it became a constant in the code or whatever, right? From the program context, you might also infer some additional optimizations there. And it can also fold multiple of these guards together. So they just, so you only need to be checked once.
It might make sense to use another scene positive value to check the other branch as well, right?
Yes, it totally makes sense to do the same thing for the other branch. We actually in Truffle also have primitives to do this kind of pattern. So the one thing I've shown here is the branch profile pattern, but we also have a condition profile pattern that you can just use straight out of the box. So we also have a Truffle DSL that is a small DSL that allows you to specify speculations in a simpler way. Won't have time to go into much detail there today, but we have a lot of tools on top of that, but they all really boil down to these kind of patterns. So Truffle DSL produces Java code in the end for you to make some of these patterns simpler. But they all fall down to having a compilation file thing in there, express it, deoptimize when the guard is false. So the pattern is just the same. So it doesn't add new things to the system.
But you do need to add these specializations as a interpreter writer, right?
Yes. That's not automatic. Yeah, in Truffle it's not automatic.
Is there a way to make that? I mean, or is that on the roadmap, or is that too?
No. There are too much. So we do some evaluation of our specializations. So we have tooling to find out whether specializations are used or not used at all. So we can actually remove them if they are not used. But actually, this is where the ingenuity of the Truffle developer comes in, because you need to find out what actually makes sense to specialize on. And there is a big leap on arguing this automatically, right? Because there's a lot of information. It depends on what you expect ASTs or programs to look like, what patterns do you expect, what is common, and then you need to ask a question, is it really worth it? So is it really worth to pay the price of a deoptimization? And that heuristic has not been built yet to find this out automatically. So we have built all kinds of tools to make this easier, this process. Yeah, but I don't think it can be automated so easily. In a method-based compiler, there are trace-based compilers like PyPy that do a very similar thing that we do, but they use a trace-based compilation, where they can actually the specialized traces out of the compilation, and there you can you have some form of automatic specialization. This has ups and downs. We have people working with PyPy with automatic specialization. I personally think that manual specialization is best because it's a little bit more work, but it also gives you more control in the end. And most of the time you want that control.
So another thing with Truffle, at least in the beginning, what I remember is what it was especially useful for dynamically typed languages, where you would do type specialization on arguments of operators, for example.
Yes,
is that, go ahead.
Sorry, I interrupted you. So yes, Truffle was originally developed for dynamic language because JavaScript was our first language. So there you can see it in Truffle in a lot of places. Our frame abstraction, for example, is very much built for dynamic languages. So you can add additional frame slots at dynamically at runtime and things like that, right? But this also has a trade-off because that dynamism or has some cost in the interpreter, for example. This is something we're currently working on to make our statically typed languages more efficient in the interpreter, because we want them to have faster frame accesses and things like that, because they all know that they are typed, right?
Right. Yeah. So the question is Truffle beneficial for statically typed languages if you don't do type-based specialization, for example, right?
It is definitely not slower. You can do everything the static optimizer can do, and you can do more because you have the profiling feedback that you can fill in. A lot of static compilers also allow you to do some profile guided optimization that do similar things. I think yeah, it is possible. So one thing in Truffle we have this. In the beginning, this interpretation step that is obviously much slower than a statically natively compiled language in the beginning. Over time, we reach the same or sometimes better performance than them. But we also want to, we are also working on a mode where you can actually AOT compile the Truffle ASTs and include it in a thing that we call auxiliary image that you can just store next to your application. It's our way of doing AOT compilation for the static languages. So we also want to support that in Truffle in the future. This is something we're currently working on. For example, the native extensions we include in the languages, they can often be ahead of time compiled. They don't need to be run at runtime. And then you save a lot of time.
But ahead of time compilation based on an interpreter.
Yes. So you build up we build up the AST. We have one more method we call on the AST to prepare for AOT, and then we initialize all the frame slots, and then we just trigger the compilation for those AOT. And then when you start the application, it's already readily compiled.
Okay, so that should be easier than building a custom compiler.
Yes, and
because,
then
right?
yeah, but the static languages can then also de-optimize. You can use interop on them, so there is also some benefits to going the route through that interpreter.
Right. Okay.
Okay, let's move on. So composing languages. So this is the thing I'm talked about, is when you actually want to mix multiple languages together. I have just built a very artificial example, so it actually fits on a slide, just to give you an idea how this looks like when you mix and match multiple languages. So for example, you can just access this Java type here, const big integer in JavaScript. So you call this java.type, java-lang math big integer, and then you have a handle on the big integer class in JavaScript. And then you embed all of this in Node.js. So you could define your Node.js application. With this app.get, you basically specify that the root of the application of the HTTP server will call this function, which gets a request and a response. And then we just write some plain string hello world from GraalJS into that text. So there is no, there is just JavaScript there for now. And then we just use that big integer. You can use that big integer just like any JavaScript object. So you can call static methods, you can call instance methods, you can functions, you can print to string, you can do all the things you would expect from that object. But it also tries to be as much as possible a JavaScript object. So even Java objects that are passed into your application have prototypes, for example. They really try to emulate the full semantics of a JavaScript. So if you take a foreign object of another language and you pass it in some other function, you can at least expect it has some reasonable behavior. And then you can, for example, also choose to just produce a plot using R. Here we embed some R code. You can also do that. You can also load it from a file. You can also pass in additional data structures from JavaScript, from Java into R, and mix and match that. So these demos are really just there to show you what's possible. In practice, you would have some bigger library and some other big library, and you want to like compose them together because they are just not available in that other language. For example, these days, I think JavaScript has a big int abstraction, so you would not need the Java big integer anymore, but it's something that you can use to close the gaps between the languages. And the important thing to note here is too that we can actually optimize across the boundaries here. So if our code is accessing JavaScript objects, we can optimize the accesses directly. And how does this work? With the knowledge we already have, it's also, so we have here a simple JavaScript property access. It just writes to a variable A and reads from a local object value with the property name prop. And what happens now if that, normally we would just produce a property read in JavaScript, you would implement your Truffle node for it, it would be optimized and so on. But what if this object is not a JavaScript object? What we would then do is we basically would insert interop nodes for this particular case. So if the object is not a JavaScript object, we would insert a guard for that. Then we would insert an interop read. And that interop read performs message resolution to insert the semantics of other languages. So we basically ask the object, without knowing where it's coming from, give me a way to read yourself. And in this case, we have a Python object coming into JavaScript. So we just insert a Python read. And now you can also see how this can be optimized together, because now we just perform partial evaluation on a new AST again. And it just naturally optimizes together in the same semantics, and the compiler can do all kinds of optimizations across these nodes. What happens if multiple languages come in? Then we just chain multiples. And at some point, we need to actually cut off, just like with any inline cache, you need to at some point say, oh, this is now a virtual call, a slow path call, and then we would need to dynamically dispatch to the foreign language, to do a slow path dispatch to the foreign language. Okay, so the interoperability protocol really consists of two parts that you need to do. On the one side, you need to export the behavior of your current language to the interop protocol. And on the other side, you need to make incoming objects from other languages make fine with the language semantics. Ideally, you cover the entire language semantics and interpret this. So in order to not repeat this with every language, with every combination of language that we have, we invented the interoperability protocol in between. So languages map their semantics to the interoperability protocol and also expect values and map when they come in and map them to the behavior of the interoperability protocol. Typically, it's much more work to map the incoming values to the language semantics because the language semantics are much more rich than the interop protocol. But you can see that there are some things that get lost on the way. So this is not a 100% solution. We really try to focus on making code portable. So this is our goal. We really want you to use other language objects without knowing where they're coming from. And so they really behave like the language in the current language. And sometimes this is just not possible. One example is you pass in a Java object into your JavaScript application and you want to modify the prototype of it. We have no place where we could store that new prototype. So this is an operation that would just fail. But we always try to stay within the bounds and semantics that the language has specified. So we don't try to invent new stuff, new behavior or different behavior. So we try to interpret it on that interoperability protocol. So this is, as you can imagine, this is one of the sources of the biggest debates in our group and also between the languages. We have fun calls how to map languages, but the overall goal is really to maximize portability of code. So you can write code without knowing that this code is going to be used from another language, and it should be useful in that other language as well without knowing where it's coming from.
It seems to have sort of an object-based bias. Is that?
Yes, currently, I mean, we are extending this as we see new use cases coming in from at least 2 to 3 languages, right? And then we try to invent a protocol that can cover this semantics. It's quite surprising what you can do with this little many types and traits, as I declared here, you can do. So we have types in the interoperability protocol. They are basically exclusive. Something cannot be null and a string at the same time. Something cannot be Boolean and a number at the same time, for example. And we also have traits, something like that is object-like. We have array elements, something that is like an array, but they all can be combined. So something can have members, and something can also have array elements. Or something can be executable if it's a function. Something can be instantiable if it's a constructor, and so on. It is very object-based indeed, because
and if it's
the languages.
So you can use a closure can be an executable object.
Yes, it's just mapped to an executable.
But it can have state as well. I mean that's.
Yeah, sure. Members have state.
Well.
Yeah, the members have. You can read-write them. You can invoke functions on them to modify internal state. Yeah, but you're right. Since the interoperability protocol also looks like on the asks the object itself how to interpret itself. It is really object-oriented in that sense.
Okay, so you could. So what functional languages have been implemented in?
We have some. We don't really have many. We have only some experiments. Also because functional languages are not as popular. We wish we had more. So if you are interested in doing that, happy to support you. And we are also happy to extend this protocol whenever we see fit. We actually, this is already version 2, and we want to evolve this protocol. So this is not frozen yet. So we actually changed this protocol. We deprecate and remove stuff every 2 releases. So languages currently need to keep up with our protocol. But at some point, we hope to freeze it if we have a sufficient number of languages implemented. Maybe we will never freeze it, but yeah. Okay, this is not done. That's what I'm saying. Also, the cursive stuff is currently in development. So, okay.
Go ahead.
Then, how do we compose tools? I also do a small excursion there. So, how can you use Chrome Inspector development tools and just step from one language into the other? And the way this works is basically we have a Polyglot instrumentation framework underneath that uses a concept called node tagging. So assume we have this JavaScript function, simple JavaScript function, and we have the according AST nodes to it. And then we ask the languages to annotate the individual AST nodes. For example, the foo node itself that represents the function can we just annotate as a root. We can, this one assignment statement, we can set to statement, and in JavaScript, it's also an expression. And then we can also map these individual operators as expressions in JavaScript. And it's really surprising the amount of things you can do with just this basic knowledge, right? You can implement the debugger by just instrumenting all the statements and roots, because with the roots, you know when you step in or when you step out. With the statements, you know when you step over where to stop, right? So with that information from the language, we can do a lot of things. But this is not, we're not just only doing that. We also have an API to look up scopes. So at any point in time in these instrumentable nodes, you can look up the current local variables and read and write them using our scoping API. That also works just with our interoperability protocol. So our scopes is just a list of these interop objects, and you can read and write to them as you want them. And there are also some extensions a debugger wants to have. For example, a debugger just doesn't want to look at an object from a normal perspective, but it actually wants to inspect it. So you really want to see the private fields and stuff like that we normally don't expose in interop. But in a debugger, you want to see all the private fields sometimes. So tools have access to these views. And a language just implements this interface in its node, instrumentable node, and then you can say which nodes have this tag. And the instrumentation framework itself is language agnostic, and every tool can use it. We also have a debugger framework on top that actually allows us to implement multiple debugger backends with the same logic, because it's actually also quite some significant work to implement the debugger, turns out. So it paid off to have our own abstraction there as well. So it should be rather easy to add new backends to that. So what Polyglot tooling do we currently have available? We have the Chrome Inspector integration that allows you to debug and profile across languages in Chrome Inspector. That's also the thing we already use in production very much. For example, Oracle NetSuite is using that to make application server scripts debuggable. So that piece is very successful. And we have a CPU sampler. We also have a GraalVM integration. We provide coverage results across languages. We built a Visual Studio integration, so you can get started with Polyglot language development a little bit quicker. You just install that Visual Studio code integration, and GraalVM already runs your code. We built a language server protocol abstraction tool in Truffle that gives you a way to take a static language server protocol and we add dynamic autocomplete information to it. So whatever you can see at runtime. The way we do this is we run the application in the background to collect the symbols that would be available at this particular location. So it's the real information. And we can do running that in the background because I will talk about this in a bit. We can actually sandbox the execution there. I could do an entire talk on this one. And we have the thing that we call GraalVM Inside that allows you to do this kind of instrumentation. So you can attach your own code or your own script code to statements, roots, and functions. It's very similar to the Polyglot instrumentation, but now you can also write normal JavaScript code to do that. Or you can basically use JavaScript code to instrument Python code if you want, if you're crazy enough. And for our Java implementation, we of course also want to support JDWP. But currently, the JDWP protocol is not very suitable for other languages, so we are not quite sure how far we can go there. Okay, embedding. So we built an API, a Polyglot embedding API that allows you to implement a language, and this should give you an idea how this works. There is many more things to know about this. It basically exposes the entire interoperability protocol also to an embedder, so you can evaluate some code here, JavaScript Lambda, you get a function back and you can ask it whether you can execute it, and then convert the values to Java values. And the important thing here is the Java code itself is language agnostic, but the string literals here, they can be language specific if they need to be. For example, the same code also works with R, with Ruby, with Python, but you don't really have a static dependency on a language. You only have a dependency once to this Polyglot embedding API, and this allows you to access all these languages. And important to note here too is like we create this context object here, and the context is basically the state of the entire guest application. So you can spawn them, you can have multiple JavaScript applications running in one host application.
So can such a Lambda have bind variables in the context? I mean, these are closed Lambdas, but
yeah, sure. You can also directly write to the top scope of a language and read top scope values from a language. There's actually an API for that.
Okay. Oh, also cross language.
Yes, also cross language. So the API looks like context get bindings for JavaScript, and then you just say put member, and then you write into the top scope of that language. You don't need to know the script. But certain things
can make closures that capture these things as well.
Not language agnostically yet, but I have a feature request for that. Yes.
I see, because that's what I meant, right? I mean, instead of x plus 1, you have y plus 1, where y is some variable that is referring to the outer context. I mean, could you, or do you have evals? Fragments have to be closed.
No, they are not closed. They have access to the global object, just as like normal JavaScript programming. That really depends on the language, right? R has a list of packages in the background where it looks up symbols in the outer scope, right? Ruby has
only the outer scope. I mean, if you have a sort of deep nested scopes, would you?
We would look up all the scopes here, of course.
Okay.
It's just normal JavaScript code that you would run in this situation. It covers the full semantics. Okay, right. Then sandboxing. This is something we are currently working on. Is we want to run code in there, and then we want to restrict all kinds of criteria for it. For example, we want to restrict the maximum CPU time it's running. We want to restrict how many stack frames you can use, how many threads, how many statements you can execute, for example. That's actually pretty useful because it's a very deterministic thing a user can understand. And also we want to support maximum heap memory that the context is needing. Some of these sandbox features are already in, some of them are currently in development. The ultimate goal of these features is that we really can run untrusted code. Obviously, we need to go at great lengths with the current speculation, spectre attacks, and so on to make sure that this cannot happen. For example, for this technique, we allow to spawn an isolate for each individual context. Isolates are a thing in native image where you can create your own separate heap area for the running context. And that has its own GC and so on. And we can also, using some additional security mechanisms, protect that memory area to avoid spectre attacks in that situation. We are not, so it's probably not going to be web untrusted, but for application server, it might be good enough. So this is really an open question. We want to explore how far we can push this to run untrusted code in the same process. And if that all doesn't work, you can also decide to spawn a process for each context, which obviously is slow and you only really want to do when you have very high security constraints, like in the web situation.
So is mobile code an option where you actually send code to another machine?
Well, we didn't explore that yet. Also, the spawn process part is not yet implemented. the spawn isolate part is half implemented. So it's really I think we're actively working on, but the goal is run untrusted code, maybe also on remote machines. We don't really have a use case for that so much at the moment. Okay, so what languages are we currently developing? I already talked about the Oracle developed ones, but we have really cool externally developed ones too. We have NVIDIA CUDA integration, where you can run CUDA kernels and then access the GPU data structures or arrays directly and modify them in your languages. This also works using interop, for example, so you can just access these arrays using interop. That's a very neat feature and easy to and developed by NVIDIA directly. Then we have Truffle Squeak, which is implemented by Fabio Nifas, who is also talked today already. It's our Smalltalk implementation. I just see that the logo is cut off. I'm sorry for that. Then we have Goldman Sachs building their internal language, Slang. It's not a public language. We have a simple object machine developed by Stefan Maar, it's really a research vehicle. But if you wanna plan to do research on Truffle, that is something to check out. And the last thing, the new addition is Yona, which is actually a reference implementation that is already built on top of Truffle. So they really have gone all in with us. I'm really happy to see that coming too. Okay, so what are the performance expectations you can have from Truffle interpreters when they are properly implemented and optimized? So in terms of peak throughput, compared to the best-in-class reference implementation, if it's a language that is already compiled, we are typically within 2x slower or faster. It really depends on the benchmark. It really depends on the language. So I cannot make any general statements here, but this is the range we currently see. For languages that are only interpreted currently and have no compilation, you get that benefit of compilation, which can be everything between 1 and 100x faster. For example,
so
R
what
is not
what do you mean with only interpreted?
Languages like R, like R only have an interpreter. They don't have a compiler. They have some experimental compiler now, but
outside of Graal.
Outside of Graal, best-in-class reference implementation. So this is the outside world. Yeah.
Right.
Thanks. Okay, in terms of startup and warm-up speed, this is something where we definitely need to work on, as I already talked about a bit, about exceptions for contour flow. And this is where we are typically within 1 to 5x of reference interpreters. Sometimes because we collect too much profiling information and that slows us down. Sometimes because of these exceptions. But we recently added multi-tier compilation. So we have a very fast first-tier compilation that gets away from the interpreter as quickly as possible. We produce some partially validated code as quickly as possible. And that actually gave us very significant improvements recently in warm-up. So we're not that far away anymore as we were previously. This is an active area of improvement, and we expect to be much better in the coming releases there. And the good thing about this, you don't need to do much there. Mostly you get these benefits from us optimizing this for your language. So this is really something I need to stress here. All right, memory footprint, I already talked about. Sometimes we profile a little bit too much. AST nodes could be compressed using a bytecode interpreter, for example. Bytecode interpreters have a little bit better footprint. It's also an active area where we try to improve. We also try to use some EOT native image compilation tricks to get our memory footprint down without having to change the languages. We also actively work on this. But peak throughput is something where we lately don't invest too much in because we are actually pretty satisfied. I mean, there are still things to do, but I think we have shown that peak throughput is working. So the important thing is it is not hard to be faster on peak throughput, but it is very hard to be always faster as the reference implementation. And ultimately, that's our goal.
So cold start is an important.
Yes, in practice it is for user experience. I mean, for server application, it's not so much, but if your server application needs 5 minutes to warm up or 20 minutes, then you also waste a lot of resources, right? So you don't want to do that. So you want to warm up quickly.
So ideally, are you saying this is mostly for server applications, or are you also targeting sort of end user?
So since our
applications, or-
interpreters are a bit slower and our compilation is currently slower than the specialized VMs, the specialized VMs with compilation, they typically beat us there. Like V8 is faster on the first execution than we are, but when you warm it up, we are as fast as they are. It is really hard to beat an assembly optimized hand-tuned interpreter, but we have taken up that challenge. So without actually needing to hand-tune it with assembly, without tricks in the background. But yeah, so for client applications, we are not as good. The thing we are currently working there is we try to persist all the ESTs, the sources, and the optimized code to disk, and then quickly load it so we don't need to redo the warm-up. So you basically have something like a profiling run, and then you write everything out to disk, and then afterwards you very quickly load it, and you're already warm. So this is the approach we are currently going for. There is experimental support for this in 23, and we will improve that feature over the next months.
then you also have native image, are you going to use that?
This only works on native image because we actually need to persist part of the heap, and then we'll need to load it very quickly. We implemented a feature called native image auxiliary images, just for that purpose. Would be another talk to go in. I had some slides in for that, but I had to cut them.
We are far exceeding the 40 minutes, right? So,
yeah.
but you're almost done with your talk? I mean, so...
Yes, I'm almost done. That's the last slide. Yeah. So how can you help us? Try run Polyglot on big workloads and give us feedback. Explore Polyglot use cases with us. It's exciting to being able to do things that you weren't possible before. Use libraries from different languages. Start implementing your own language or tool. Just go to our website. We have information there how to get started. Be an advocate for, if you don't want to do any of these things because you don't have time, at least be an advocate for language specifications. So if your language doesn't have a language specification, ping them. Tell them you need a language specification. There are huge benefits for the language ecosystem there for them, and it's also a huge benefit for us being able to implement these languages in a much more direct way, and we don't need to reverse engineer reference implementations. Also be an advocate for sane native extension protocols. That's also would be very helpful to us. And we have a really active Slack community. If you want to join if you have any questions, you want to start getting going with a language on your own, just join us there. I'm typically there. There are a lot of people there answering your questions. That's all.
Thank you. Any questions? Torsten, did you have a...
No, I didn't. Sorry, there was some interference.
Okay. Right. So talking about specification. So we actually did some experiments with using Truffle and Graal to implement DINSEM. So that's a specification language, a dynamic semantic specification language. And the experiment we did is write a Truffle interpreter for DINSEM. And in DINSEM, you would then write a dynamic semantic specification, and then you would interpret those specifications of interpreters basically. And the experiment was, can we get rid of those two levels of interpretation? And the results were encouraging, but we're not there yet. But the goal was, or I would still like to get there, is can we just have a specification and get an implementation from that on the Graal platform, right? But you wouldn't have to go through defining or implementing the interpreter, just have your formal specification.
Yeah, I mean, it depends on the formal specification, I think. If your formal specification stabilizes or is not too dynamic, right? Or ideally AOT compilable, then you can unroll the first interpreter level very quickly with our AOT compilation, basically. And that would maybe be, and I think I was in touch, how is the main author, what's his name? Yeah, Flood. I was actually talking with him, and I was recommending him that he first uses this separate these two interpretation steps. So one step that tries to figure out what the structure is, and then the unrolling of the actual structure. But I was not too involved in that project. But it's a very interesting one. Yes. It would. Did you explore to generate Java interpreters from that?
We started with that, yeah, but that was somewhat cumbersome. So then we went for an interpreter in the first place, and I think that was an interesting experiment. Of course, it also makes sense to generate Java interpreters.
Yeah, ultimately, I think you want to get rid of that meta compilation step. So you will, and so that's also the reason why in Truffle DSL we also generate Java code, and we don't do it generically, right? Because we care about interpreter performance, and that would be really bad in that situation, right? So.
Right, but I mean the promise is that you can get compilers from interpreters, right? So why not meta compilers?
Yeah, true, totally.
Right. I mean, no, but you're right. People are encouraged to attend the student research competition. Any questions from the audience? We've been chatting here. There's another plug for. Benoit also did an experiment in that direction, right?
Yeah, exactly. We did something very similar to you, Wilco, but not by interpretation, but by compilation, such as we can get a language interpreter on top of Truffle. But it was pretty hard to use all the benefit from Truffle from the meta language directly. It was very difficult to tune the interpreter and to make sure that we can generalize to any specification.
How did you figure out how to do specialization?
Sorry?
How did you figure out how to do specialization in that work? I need to read that work.
Yeah, that's the kind of thing that was very difficult to generalize from one language to another one. So that's why sometimes that was very good and sometimes that was very bad, and having a generic approach for this was not easy.
So did you try to make this part of the specification? What kind of specialization you ultimately want to do?
Yeah, it's exactly what we are working on. What we need to know in the specification in order to be able. But we are not also really keen on all the stuff that happen in Truffle, so there is a lot of magic still for us, so we are still learning on it.
Cool. You know where to reach us. We can also have a chat anytime if you want.
Definitely. Thank you so much.
All right. Any other questions? So what do you work on personally? Or do you work on all of this?
So my part is the Truffle framework itself. I also responsible for this Polyglot embedding API. I also personally maintain the Truffle DSL parts. And I no longer work much on languages. My part is mostly telling the languages what to do, which interop protocols to adopt, organizing all that, resolving disputes between the languages when they cannot find common ground. This keeps me quite busy.
The languages in the Graal team. I mean,
in the Graal team, but also in the community. I also try to support them as much as I can. We also work on some, especially we have a big warm-up effort going in the group currently to really make our warm-up performance much better. This is a main focus. I personally also work on this persistence of code. This is one of my ideas, and I'm pushing at that.
Right. All right. I think we should close down. We spent the full session, 80 minutes. That's it went by pretty fast, right?
Yeah, I timed it with 40 minutes. I should have fit it into 40 minutes, but yeah.
Well, I may have distracted you a bit. So before the stream closes, let me thank you, Christian, for your talk and for answering.
Thank you for having me.
All the questions. And Thank you.